Assalamualaikum and great day everyone. My name is Putri with my student number as 2023-414638 and currently in my second year fourth semester. Today, I'm going to present to you two of the subtopics exist in electricity and magnetism for Physics 568. So, for the first subtopic of this course is vector calculus, which is in chapter 2 in this topic. Let me first explain to you the meaning of vector. As we all know, vector is a quantity that has both magnitude and direction. So, this is several examples of vector that is happening in our real life, which are displacement, velocity, electric field, as well as the magnetic field. For vector, it is customary to represent a vector by a letter with an arrow on top of it, such as A arrow and B arrow, or by a letter in boldface type such as A bold and B bold. Indicate a component of a vector by a subscript. For example, AX in the X component of A. I will explain to you only a little bit about scalar quantity, which defined as a quantity that has only magnitude. For charge, time, mass, energy, and electric potential are the examples of scalar quantity exist in life. Now, I will explain to you about unit vector, which defined as a vector that has a magnitude of exactly 1 and points in a specific direction. It is used to indicate direction only, without affecting the length or scale of a quantity. For the magnitude of vector, it defined as the magnitude of a vector is the length or size of the vector, representing how much quantity it has regardless of direction. It also has the addition and subtraction of a vector, which I assume that all of you may be familiar with it. Let's talk about the position vector and distance vector of the vector calculus. Position vector is when the location of a point in space relative to the origin, x, y, z, 0, 0, 0. It points from the origin to a specific point and describes both direction and distance. Meanwhile, distance vector is when the distance vector is the displacement from one point to another. Application is also familiar, which we have the dot product as well as the cross product, where the dot product will specifically get a scalar product and the cross product will specifically get a vector product back. And this one is the multiplication of a triple product for both scalar and vector product. Now we will be moving on to the coordinate systems that classify into three categories, which are Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Cartesian coordinates consist of x, y, and z. Cylindrical coordinates consist of rho, phi, z, and spherical coordinates consist of rho, theta, phi. Actual elements are infinitesimally small pieces of length, area, or volume used in integration of curves, surfaces, and volumes in space. They are essential when calculating electric fields, flux, and charge distributions. So, Cartesian, spherical, and cylindrical have their own differential element. The del operator, denoted by the upside-down triangle called nabla, is a vector differential operator used in vector calculus. It acts on scalar or vector fields to describe how a quantity changes in space. When applied to a scalar field, it gives the gradient, indicating the direction and rate of increase. When applied to a vector field, it can produce the divergence, which measures how much the field spreads out from a point, or the curl, which describes the field's rotation or circulation. So, del operator has divided into two different parts, where the question provided will be in either scalar or vector, which the scalar one are gradient and the Laplacian one, meanwhile vector question will be in a curl or divergent questions. So this one is the formula for gradient of del operator for Cartesian, cylindrical, and spherical coordinates. This one is the formula of divergence of a vector in a del operator for Cartesian, cylindrical, and spherical coordinates. So this one is the formula of the curl of a vector for Cartesian, cylindrical, and spherical coordinates. So this one is the formula of the Laplacian of the vector for Cartesian, spherical, and cylindrical coordinates. Now we will talk about chapter 3, which is the static electric field. A static electric field is an electric field produced by electric charges that are stationary or not moving. It represents the force experienced by a test charge placed in the space around the stationary charges. The first one that we will learn in static electric field is the Coulomb law. Coulomb's law describes the electric force between two stationary point charges. It states that the force is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. This force acts along the straight line joining the two charges and can be either attractive or repulsive depending on the sense of the charges. One is the electric field intensity. Electric field intensity is a vector quantity that describes the strength and direction of the electric field at a specific point in space. It is defined as the force experienced by a unit positive test charge placed at that point. The direction of the electric field is the direction of the force that would act on the positive test charge. The greater the electric field intensity, the stronger the force on the charge. It is measured in newtons per coulomb or volts per meter. Consequently, the electric field due to a continuous charge distribution is calculated by summing the electric fields produced by infinitely small charge elements spread along a line over a surface or throughout a volume. Since the charge is not concentrated at a single point, integration is used to find the total electric field at a specific location. The distribution can be linear, surface, or volumetric, and the resulting electric field depends on the geometry and distance from each element to the point of interest. Electric flux density, also known as electric displacement field and denoted by bold D, is a vector quantity that represents the amount of electric flux passing through a unit area perpendicular to the direction of the electric field. It relates to how electric fields interact with materials and considers the effect of the medium's permittivity. Electric flux density is directly proportional to the electric field intensity, and the permittivity is the permittivity of the material. Electric potential is the amount of work done in bringing a unit positive test charge from a reference point, usually infinity, to a specific point in an electric field without any acceleration. It is a scalar quantity that represents the electric energy per unit charge at a point in space. The unit of electric potential is volts, where 1 volt equals 1 joule per coulomb. A higher electric potential means more electric potential energy for a positive charge placed at that point. Now I will present to you all the Maxwell equations that exist in static electric field, which two of them are the Gauss's law and then the other is Faraday's law and Ampere's law. For the first equation, this equation explains the relationship between electric charge and electric field. It states that the total electric flux passing through a closed surface is equal to the total free electric charge enclosed within that surface. In simpler terms, it tells us that electric charges are the source of electric fields. Positive charges emit field lines, while negative charges absorb them. This law is often used in electrostatics to calculate electric fields in cases with symmetrical charge distributions. The second equation, this law tells us that magnetic monopoles, isolated magnetic charges, do not exist. In contrast to electric fields, magnetic field lines always form closed loops. This means the total magnetic flux coming out of a closed surface is always zero. Whatever goes into the surface must come out. It reflects the fact that every north magnetic pole is always accompanied by a south pole and vice versa. On to the third equation, which is the Faraday's law. This equation describes how a time-varying magnetic field can create or induce an electric field. It shows that if the magnetic field through a loop or area changes over time, a circulating electric field is created around that loop. This is the principle behind how electric generators, transformers, and inductors work. The negative sign indicates the direction of the induced electric field opposes the change in magnetic flux, which also known as the Lenz's law. Last but not least, the Ampere's law, where this law shows that magnetic fields are generated by electric currents and by changing electric fields. The original form of Ampere's law only included current, but Maxwell added the displacement current term which accounts for changing electric fields, especially in capacitors where there is no conduction current. This correction is essential for predicting the existence and propagation of electromagnetic waves like light. To sum up, these four equations describe how electric and magnetic fields are generated and how they interact. They form the foundation of classical electromagnetism and explain the behavior of everything from static charges to electromagnetic waves like light and radio. So that's all for this video. Thank you.